So here's the entire electromagnetic spectrum. And visible light is just this little part in the middle. This little section right here in the middle. And we brought it down here and then we expanded it so that we could see it a little better. And up here we have an illustration of, kind of a representation of the wave. And so over here we have short wavelengths. This is high energy. And here's the scale that shows us the wavelength in meters. These guys are 10 to the minus 15th meters. And over here at the low energy long wavelength, we have 10 to the 5th meters. There's electromagnetic radiation that has wavelengths longer than a mile. Big, long wavelengths. Very low energy though. So let's look at the middle here first, visible light. So we have this continuum here. And I forgot to write something on a previous slide, so I'll do it here. We've got red, and it goes into orange, and yellow, and green, and blue. And there's this mysterious color called indigo in the middle there, and violet. And it's always in the same order. If you've ever seen a child draw a rainbow, a lot of times they'll just draw the colors in there randomly. And you can tell they're meaning to draw a rainbow, but you look at it and you're like, something's not right about that rainbow. What's wrong with that rainbow? The colors aren't in the right order. An actual rainbow, the colors are always in the same order because the prism separates them by their wavelength. And the way you can remember the order is by the initials. I'll put it up here. Roy G. Biv. Kind of like somebody's weird name. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. That's the order that the colors go in. So the red light has the longer wavelength, which is the low energy. And the violet light has the higher energy, which is the shorter wavelength. And there's this range. They range from 400 nanometers to 750 nanometers. Compared to the entire electromagnetic spectrum, it's a very tiny range. And then we're going to talk about these other types. The spectrum is divided into different sections: ultraviolet radiation, X-rays, gamma rays, infrared radiation, microwaves, and radio waves. And you've probably heard of most of those. So gamma rays, those have the shortest wavelength, and so they are the most energetic. They're very high energy. They're produced by the sun and the stars, because the sun is a star, right? And also some unstable atomic nuclei on the Earth will also make gamma rays. Gamma rays can be extremely dangerous. Okay, atomic bombs, one of the most dangerous things about them is the gamma rays that are given off. They definitely can damage tissue. X-rays are less energetic. They have a little longer wavelength, and yet they still carry plenty of energy and can cause damage to biological molecules. Both of these have uses in medicine. X-rays, of course, we've probably all had at least one X-ray. They can X-ray your teeth and see if you have cavities or if your wisdom teeth are impacted, see if your arm's broken. X-rays are very, very useful, but too many X-rays can cause cancer and other problems. I think, there's a little blurb in your book, and if you're interested in this, I'd encourage you to read that whole thing. But X-rays and gamma rays can be used to kill cancerous tumors. And this is an illustration of what they will do. They'll aim radiation at the tumor from multiple directions, especially for a brain tumor where they can't go in and remove the tumor. They'll send the beams of radiation at many different angles. Well, why not just zap it at one angle? Well, because it also damages the healthy tissue that it goes through. So by sending this radiation in lots of different directions, they can minimize the damage to the healthy tissue and maximize the damage to that tumor that they want to get rid of. And the radiation tends to damage mostly those rapidly reproducing cells, the ones that carry genetic information. And so it can either stop the tumor from growing, or it may kill it entirely. But the healthy cells also incur damage, okay? And so that's why, some of the side effects of radiation therapy can be hair loss and issues with your fingernails and other parts that are rapidly growing. So, there's a risk-benefit in pretty much anything. I mean, the radiation therapy itself could cause another form of cancer. But if you didn't have the radiation to get rid of the first cancer, maybe you wouldn't even be around to get the second cancer. And so there's a risk and a benefit to every sort of medical treatment. But that's an interesting application of radiation. Ultraviolet light, we've heard a lot about. Been a lot of campaigns to inform us about the dangers of sunburns and skin cancer. Ultraviolet light comes from the sun. It can also be generated by ultraviolet lights. It's less energetic than X-rays, but it can still cause damage to biological molecules. And if you've ever gotten a sunburn, you know that. You're out in the sun too long, and I can get sunburned pretty quickly. Go out in the sun, and then your skin turns red, and it hurts. Yes?
When does the wavelength stop being able to travel through solid objects? Does UV light still travel through our bodies, or does it stop when it becomes a object?
UV light can travel through, I know I can travel through some clothing. I mean, you can get sunburned through a white t-shirt. And that's why there's been all these, clothing manufacturers are selling clothes that are specially designed. They have an SPF of 50 or something, and they will block. I got sunburned under an umbrella at Pismo once. I sat in the shade the whole day, and I still got sunburned because it wasn't one that had a coating on. It was just fabric, and enough light came through the umbrella that I got sunburned. So ultraviolet light can go through some things. But things like gamma rays can go through solid objects. They can go through concrete brick walls. And X-rays, when you get a dental X-ray done, they put this heavy lead apron on you to shield the rest of your body from the X-rays. And those are, quick, low-energy X-rays. So X-rays can also go through solid things. And that's why they're useful for taking pictures of your bones, because the X-rays will go through your skin. It's a good question. Visible light is the light we can see, and that does not damage biological molecules, and yet it does have an effect on biological molecules. We can see because the molecules in our eyes rearrange in response to the visible light that hits our eyes. And our brain interprets that rearrangement in a way that gives us vision. So it's the interaction of this light energy with the molecules in your eyes. It's really pretty amazing when you start thinking about it. Past the visible light is infrared light or infrared radiation, because you can't really see it, and usually we think of light as something we can see. But when you place your hand near a hot object and you feel the heat coming off of it, that's infrared radiation. Your body is giving off infrared radiation right now. All warm bodies, including humans, emit infrared light or infrared radiation. And we can't see it, but there are sensors that are sensitive to it, and so we can use it to create night vision technology. Question?
You can see like heat waves. A hot metal object, and you can see kind of.
Yeah, that's infrared. In fact, here's a picture. So on the left is a normal photograph of a man with his dogs, and on the right is an infrared photograph. And so you see the warmer areas as red and the cooler areas as being dark blue.
I was talking about your own vision. You see like a really, really hot metal object out in the
Oh, and
sun.
you see the little waves?
You see like clear waves coming off of it.
I see. Yeah, that's a great question. And that's the same thing that happens when you're driving on the highway in the summer and it looks like there's water on the road, but there isn't. You get up there and there's no water on the road. What happens is the heat, air has a different density when it's warmer or cooler. And so near a hot object, the density of the air is less, and so it bends light differently. And so you can actually see a kind of a Ripley effect, a disruption in how the light comes through. A little bit like when you look at an aquarium. You can get some really weird optical illusions going on when you look through in an aquarium because the light bends through the glass and through the water differently than it does. So on the highway, what happens is the sun comes down on the black road, which absorbs all this energy and gets very, very hot. If you've ever walked barefoot in the summer, you know that black asphalt can burn your feet, right? It's really hot. That heats the air above it. So you've got this layer of warm air, and then above it you've got cooler air. And you see the sun coming in, and you see it reflecting off that air in a different way than it would if there was no hot air there. And so it looks like water, because water reflects the light like that. And the asphalt doesn't. The asphalt normally absorbs it, but because of it, the different density, it refracts and bends the light differently. Does that answer your question? It's a good question. So, the night vision technology is pretty cool. And all that is looking at infrared radiation instead of visible light. We can't see it directly with our eyes. We can see how it, how the heat, the thing I just explained. We can kind of see that, but we can't see infrared directly. But we can develop sensors that do. And so you look at this picture, and what do you notice about this dog's nose?
Cold.
It's cold. And there's the other dog's nose. And here's this dog's nose. So this seems to confirm what we've all grown up hearing, that a healthy dog has a cold nose, right? But you see his eyes and his mouth and his ears are warm. And you can use technology like this to find people hiding in the woods, because they may be, covered, but there's infrared heat being given off from their bodies. And so with night vision like this, you can spot them anyway. Microwaves. These are the microwaves that are in your microwave oven. And they're also used for radar. Microwaves are efficiently absorbed by water, and so they cause water to heat up, but most other substances do not absorb them in this way. And so you put your food in the microwave and it's got water in it and it'll warm up. You put a plate in there that's microwave safe, does not have components that are sensitive to microwaves, and the plate doesn't get very warm. Now, if you've made the soup in the bowl really hot, the heat from the soup will make the bowl hot, right? But there are other dishes that are not microwave safe, and when you stick them in the microwave, the plate itself gets crazy hot. Okay, you shouldn't use those in the microwave. Eventually they're going to break. But that's kind of, in a nutshell, how microwaves work. So microwaves have longer wavelengths and less energy than infrared. Yes?
I read somewhere when you microwave water, it changes the molecules.
It causes the molecules to vibrate more. Okay, and temperature is kinetic energy, this vibration of molecules. And so the microwaves come in and they cause the water molecules to vibrate more, which makes them warmer. I leaned on the computer. That was not a good idea.
What is it doing when you put metal in the microwave? Why does it start popping?
That's a good question. I'm not exactly sure about that, but I know metal in the microwave is not a good idea, and it does cause sparking and arcing and all kinds of bad stuff. I can't answer that one off the top of my head. Small amounts of metal, like for a while we were trying to pop popcorn. You can actually pop popcorn in a paper bag in the microwave. You don't need the fancy stuff that they sell. You can staple the bag shut, fold it over, put a couple staples in it, and the two little staples won't have any trouble in the microwave. But yeah, if you put a fork in there or something, not a good idea.
What's happening when you put have you seen like the highlighter? You put a highlighter in and it becomes a gas. Is that bad for a microwave? Would that mess up the microwave?
I haven't seen that one.
Oh, it's really cool. Like it becomes a gas and it like floats around.
So would it be like a yellow gas? It probably
Or like
just
I saw
kind
it with
of
a pink marker.
a pink marker.
Like a pink highlighter gas floating around. I was like, I want to try that, but I don't want to ruin my microwave.
I would think it would make a mess. I would think
Is
it would.
it like giving just heat and that makes it into a gas? Is that all
That would be
happening?
my
Just
guess.
a physical change.
That would be my guess. I'm not sure off the top of my head. There's a lot of creative things you can do with microwaves. Some of them are just not a good idea. But, you know, like you put a marshmallow in the microwave and it grows, right?
Oh, okay.
Or peeps. Peeps in the microwave are fun. Soap. I scared myself to death once. I make my husband coffee, and at that time we were heating the water in the microwave. And I'd heated it to boiling, and then I got distracted, as I so often do, and I came back, and it really wasn't hot enough anymore. So I just turned the microwave on again. And to my shock, after a little while, there was this boom, and the door of the microwave swings open. Because what happens is you can end up superheating the water. So if you're going to reheat water, stir it up real good, or just get some fresh water. This is what happens when you boil the water. All the dissolved air comes out. And then when you boil it again, it becomes superheated, and big bubbles of steam will form in the bottom. And yeah, it can blow your microwave door open. It didn't damage anything, but it made my heart go really, really fast. Oh my goodness, what happened? Yeah, so there's all kinds of weird phenomenon that can happen with the microwave. And then radio waves. These are the least energetic. These are used to transmit signals. AM, FM radio. Your cell phones use radio waves. Television, other forms of communication all depend on radio waves. Could we communicate with microwaves? We could. We could.
They're just not as effective as radio waves? Is that why we don't use them? Or do you know?
Well, I do know that the longer, I think it's the longer wavelength waves travel better. Like AM radio stations, I remember growing up in Minnesota, sometimes at night, I could pull in radio stations from Texas because those waves just travel so much better than the shorter ones do. You know, the shorter ones, like the gamma rays, will go through solid objects, but they're not necessarily going to travel long distances. And again, that's going off a little bit into physics. It was very, very interesting stuff. I just don't remember all the details of it. But what our government has done is decided, okay, this range of frequencies is going to be used for this, and this range of frequencies is going to be used for this. And like, you know, with the cordless phones at home, your landline cordless phone, you know, there's the 2.4 gigahertz. Well, that's the frequency of the signal that it gives out. And when you tune the station on the radio, you're going to different frequencies. You know, 106 FM is a particular frequency which corresponds to a wavelength of that radio wave. And so that radio station has reserved that little wavelength to broadcast their signal. Because if somebody down the road broadcast on the same signal, then there would be interference and there'd be problems. So it's really, really interesting stuff, but a little beyond our class right now. So let's look at this example. Arrange the three types of electromagnetic radiation, and they're just giving us three here: visible light, X-rays, and microwaves, in order of increasing wavelength, frequency, and energy per photon. So you should have a picture of that electromagnetic spectrum in your head, and you should know which of these are more energetic and less energetic. Visible light, X-rays, or microwaves. Which is the most energetic? has the most energy and can cause damage to biological tissues?
X-rays.
X-rays. Okay, so I'm going to do the one on the bottom first. So X-rays are the most. We're supposed to go in order of increasing. So over here, X-rays is the highest energy. And what was smack dab in the middle of that chart? The visible light. And the microwaves are over here. And you may say, well, couldn't microwaves damage tissue? Well, they could, but they would damage tissue by heating up the water in the tissue. It's not that they damage the molecules themselves, but they cause heat, which could damage tissue. So microwaves are the least energetic, then visible, then X-rays. So let's relate that then to frequency. Remember those two waves, the slow yellow wave, slow looking, long wavelength, and the high frequency red wave. Which one looked more energetic? The red one, right? That had a high frequency. So high frequency corresponds to high energy. So the order is going to be the same for the frequency as it is for the energy. So microwaves are low frequency, and then visible light, and then X-rays. And how does this relate to wavelength? Opposite. Long wavelength is low frequency, so we switch these around. X-rays have the shortest wavelength, and then the visible light, and then the microwaves. Any questions about light? You guys ask a lot of good questions, by the way.